now the structure, how like people on YouTube should follow it.
Okay, so we are already in live, so whenever you want, Vito.
Okay, thank you very much. So, okay, welcome everyone. And today we will be doing the first tutorial of these classes. And I think that the idea of this tutorial, of this first tutorial, which is called Amber Tools, from the setup to the analysis, is mostly about the structure of the software itself. So, because there are two things that we need to do. One thing is to actually understand the software and what can we actually take out from it. Wait, someone should turn off the microphone because
sorry, it was me, Vito. Sorry.
Okay. All right. So, all right. So the idea of this tutorial is to actually understand the software, as I said. Therefore, I will go through all the steps, starting from obtaining the structure of the file to solvate the system. So the idea is to obtain the structure, solvate the system, then run the dynamics, the classical dynamics. Then I will introduce you to CPP Trajectory, which is the post-processing analysis software of Amber. And then if we have time, we also will run a QMMM calculation from the structure, from the simulation that we've done classically. All right, so for the people on YouTube, so there are three free softwares which you should download, which are Amber Tools, VMD, and Orca. Orca is for the last part, the QMMM. So yeah, let's see if we reach there. But yeah, Amber Tools and VMD are important for this tutorial. Therefore, the idea is that you should follow the PDF that I've placed in under communication, and on the next to day 5, we have the PDF of the tutorial which you can download. And therefore, either throughout live now or later on, the idea is that you will be able to, with the PDF plus the YouTube video, you should be able to reproduce this tutorial. So now, as I said before, for the people connected to our Zoom session and to our computers, this is already the structure of the tutorial itself. But for the people of YouTube, please, so the idea is that we will have 3 main folders. And inside of the initial structure, now we will first go through the PDB website, where we will download this PDB structure. And then those are the input files which you will find in each of those folders, but in your case in the tutorial. So I think this image is also inside of the PDF, so you can in the meantime you can already build this structure. Okay, so now I think that the first thing is before I go to my terminal, we'll show you the PDB website. So okay, so let's go. Can you see more or less? You can see the website, yes. Okay, so this is the protein data bank. So this is where everything, let's say, starts. And let's say that this is the website. It's a database where all the crystal structures from all the experimentalists performing X-ray, cryo-electron microscopy, NMR spectroscopy can provide the 3-dimensional structures of our proteins, or also ligands, bound structure, unbound structures, and many, many more. So this is, let's say, the starting point in order to perform a simulation. And the website itself provides the possibility to download structures, but also doing visualization, analysis. For example, let's say you can do the pairwise, you can do the alignment between 2 structures to see, for example, what is the homology between these 2 proteins, and many more things. So each structure, each PDB structure has a 4 digits code, which could be either letters or numbers. And therefore now we will be working. I decided to choose a structure that I've never worked with, so that I wouldn't be biased, because I would already know more or less how it looks and everything. So let's say I will try to do this tutorial with you, let's say with this structure that I'm not really have a strong scientific knowledge in it, because as I said, it's mainly about the functioning of the software, of the Amber Tools. So now, for the people which are in Zoom, I've already downloaded and placed this structure to facilitate. But this is the structure which we will be working on, which is a dopamine transporter between the pre and post synaptic. And so this is the three-dimensional structure. This is the transporter. So what we see here is that, for example, here we see the experimental data and the resolution in the method of which they obtain this structure. Then here we can access the paper, because I think it's really fundamental to read the paper before actually working with the structure. And then also here we see something really important, which is first of all the macromolecule itself. So here we have the transporter, then also other micromolecules bound during the crystallization, and then here we see the ligands. Okay, so let's say that the ligand that we will be working today with is norepinephrine. And so let's say that what I will do now, like I've already downloaded the structure, so I will go. So from here you can download the PDB file, and I've already done this. So now we will go to the tutorial. So we will go to the terminal, and let's access the structure. So we go to each of the people go to the initial structure, and then protein. Here we have this structure. So this is the structure as it is downloaded from the PDB. So one second. So the first part is more, let's say, a physiological description of the protein. So it tells you this is chain A, so it's a covalent, is the covalent change of the transporter. Then all the other organisms or all the other molecules bound to this structure. And then if we continue, then we will go to the let's say interesting part for the molecular dynamic simulation. So we go down. I could do it differently, but let's go instead so we don't get lost. So now I'm just going down. Here there are all until we reach this part. So here is where the three-dimensional structure of the protein starts. Where, first of all, if you have never seen a PDB, it's slightly different from an XYZ file because it contains more different components apart the XYZ coordinates. So here we have the atom index. I'm telling you this because both for post-processing analysis and for visualization, those symbols are important in order to select the correct thing that you want to study. So those are the atom index. So this continues for long until the end. So it starts from 1 and it continues. Then this is the atom type. So here there's the terminal hydrogen, for example. This Ca is an alpha carbon. This is the carbonyl. This is an oxygen of the carbonyl. This is the beta carbon, gamma, and those are, for example, the two oxygens of the aspartic acid. And then this is the residue name. So we have all our proteins, all our residues with a three-digit, three-letter code. Then this is the chain ID, or which basically belongs to all the residues which are bound together covalently. So let's say that we will get to a point where this chain A will change to another chain because it's a different structure in our PDB. Then this is the residue name, the residue number. And now this is important because it doesn't start from 1, because for example, for many papers and many structures, let's say, we want to have always the same numbering for the atoms, for the residues, because if we want to describe the interaction of a residue with our ligand, we want to be sure that we're talking about the same exact residue number. Otherwise, we get confused. Then here we have the XYZ coordinates. And then here we have other three columns, which are the occupancy, the temperature factor, but those two numbers have never worked with. And then this is the basically the atom type, but without the periodic table element, let's say. So let's say from this, if you extract this column plus the XYZ, you make an XYZ file as we're used to it. So now we continue, and until the end, let's say here we have the connectivity, but let's go to the atom again. So this is really the end of the structure. Here we have those are the, for example, those are the molecules which still belongs to chain A. Okay, so now what we will be doing, first of all, we need to recognize what is the atom, the residue name of our ligand, which is L and R. So let's keep this in mind. And now let's, I think is enough of just looking at the file. So what we will be doing now is, let's visualize it as well. So I will be opening it with BMD. Okay, so this is the structure. BMD automatically opens the structure in lines. So here, I don't know if you have ever worked with BMD, but there are many different things you can do. From the, first of all, the display to make it more visualizable. Then we have the most important thing, not the most important, but for a graphical point of view, it is. So this is the graphical representation, okay? So here, first of all, we have the coloring method. So this is just about the color itself. Then we have the drawing method. For example, for proteins, I usually work with the new cartoon because you can see the alpha helixes and the beta sheets. And in this way, it's much more elegant to visualize. And now, for example, what we want to do is to select only the chain A, okay? This is the chain A, all right? So this is our dopamine transporter. Now, since there are also molecules, ligands in this chain A, but this new cartoon visualizator is only for proteins, we were not able to visualize our ligand. So, for example, we do create representation, and now this nomenclature is from BMD. Therefore, it's something that you can find in the BMD manual. But now I will show you the main ways to select something. So you can do the res name, since in this case, which means residue name, and we do L and R. Okay. So now we still cannot visualize it because it's in the new cartoon style. So, oh, wait, sorry. So let's go to licorice, for example, and now we can, let's make it slightly bigger. Now we see this, our norepinephrine inside of the transporter. So this is the structure that we will be working on today, okay? So in order to extract only this structure, we can either do it directly from the PDB, or BMD offers the possibility to save only part or a portion of your representation that you have created. Therefore, what we will be doing is going to, so first we select it, then we go to save coordinates, and then we can select the kind of atoms that we have called. So in this case, chain A will also include our L and R res name because it's in this structure. So we do save, and we save it here. Let's call it, let's be consistent with the tutorial, and we call it chain A.pdb. Okay, and we save it. Okay, so now we have our saved structure. What we can see here in BMD is many other things. Those are all the analyses that you can perform. Here there is a console where you can actually program the things that you want to do instead of using the visualization. And there is infinite things, is a language by itself. But let's close for now BMD, and we will go back to it later on. Okay, now we have our chain A. Okay, what should we do? Let's open it first of all, and we see that now we only have this part. We go down and we see that we still have, so all these are, for example, all the water molecules that during the X-ray crystallography were still in the structure. Then there are also all those other, probably I've seen there are cholesterol and all other lipids that were still present there. As I told you, I'm not I don't know too much about this structure because I wanted to dedicate it only for the Amber tools. So we start canceling all this part, and be careful of not canceling our Allen R, which is our norepinephrine. So we remove all these things. Please stop me if you're not following, or for any other reason, please stop me. Okay. Okay, now we have this structure, which is our protein plus our ligand. So if we will open it in BMD, now there will only be those two. Now let's close it, and we begin by, first of all, what we want is to work independently on the protein and on the ligand. So the first thing is we want to get rid of the ligand and save it in his own folder. So we'll grab the Allen R from chain A, and let's save it backwards in ligand in our folder, okay? And we save it here. Sorry. Okay. Sorry. Al-NR, yes. So initial structure, protein. Okay, we have it. So let's copy it to ligand here. Why can it?
I think you have to give a name to the.
Oh yeah, sorry. Yeah, sorry. Thank you. Yeah. Of course. Okay, let's call it lig.pdb. Sorry, was a bit confused. Okay, great. So now we have the chain, and let's check. We have here we have our ligand. All right. So let's go back to the protein. Thank you again. Okay, so what we want to do is, first of all, we will begin to use all the Amber tools. So the first thing is that Amber recognizes, let's open again this one, and Amber has its own atom types. And therefore, what we want to do is to be able to make Amber recognize this structure without encountering, with minimizing the amount of errors that we want to, we can encounter. So the first thing is, the first command that we will be using is the reduce command -trim, which means remove all the hydrogens from the structure, from our chain .pdb. Okay, now in this case, usually the PDB structures obtained from the database are already without hydrogen. But a few times there are some other uploaded structure that have hydrogens. So let's compute this command anyways, and let's call it chain A no hydrogen, for example, .pdb. Okay. So if we see removed 11 hydrogens. Now we removed the 11 hydrogens actually because it removed the hydrogens of this Allen R. Now, since we already saved this Allen R, this norepinephrine, we can remove it because we will not be using it. Sorry, chain no H. Yeah, if we see now, yeah, it's as 11 atoms less. So let's remove them. Let's remove it. Okay. And now we do the PDB for Amber, which is another command, this time with 2- reduce, which basically reduce -3 means remove the hydrogen. Reduce by itself means add all the hydrogens that are missing. So in this case, we will add all the hydrogens of with the atom type of Amber. So we'll do PDB for Amber -- reduce our chain no H, and we call it amber.pdb. Okay. So let's open this amber.pdb, and now we have all those hydrogens which were missing before. So now in principle, this structure should be good for the next steps where we will solvate the structure. All right, so this is the structure. Let's remove this.
Sorry, Vito. There
Yes.
is a question in the YouTube channel. I'm gonna copy on the Zoom chat so that.
Yeah, sorry, I'm not. I cannot.
No, it's okay. That's what we are for here. Okay, I put it in the chat.
Could you? But of reason that okay. Yeah, okay. So now I've actually never used AlphaFold, so I don't know what kind of structure they begin with. But in principle, I think that in order to start from like a PDB is a structure that contains all the available information to then apply them to a force field. So either we use a PDB or a Mol2 file. I don't actually know what AlphaFold, what are the structures used for AlphaFold. For the ligand, we will go now to the ligand and I will tell you how to do it. Now, in this case, the ligand, okay, yeah, let's talk about the ligand very, very soon. So regarding, yes.
Just one comment. I was now Google AlphaFold, and apparently they have PDB files also.
Okay, yeah, because in principle is the smallest file which you can have in order to compromise everything available to be recognized by a force field. Okay, so this is why they have PDBs, and those are why those atom types are all fundamental in order for the force field to recognize the correct atom types, both for proteins and for ligands and so on. So okay, now we have what we've done so far. We have created our amber.pdb, which will be our protein structure ready for the next step. And now we go to the ligand. Okay, now we have this lig.pdb. Now let's open it. Most of the times, now what I found is that in this structure, those atom types most probably will not be recognized by the next softwares of Amber. Therefore, what I do usually in these situations is to use. So there is a software also of Amber. So it's the next one that we will be seeing is called Antechamber. So we could do Antechamber -H to see what are all the things that it can do. So Antechamber is mostly used for the general Amber force field, so for the organic molecules, in order to apply the correct charge, the correct bonding parameters, and so on. So what the fantastic thing of Antechamber is that it allows a person to move from one kind of file to another really fast, because you can input your file, you can input the file format. So let's see what are the file formats available, which can be done by doing Antechamber -L, like in open bubble. And so those are all the list of formats which are recognized. So for example, you have a Gaussian output, and you can already, without programming, you can already obtain your Mol2 file, or you can obtain your PDB. So let's say that it makes things much easier if you want to extract some information from the structure. Also, for example, let's go back here. You can even, from the PDB, you say, okay, I have the PDB structure and I want to do a optimization with Gaussian. Here you can, with these lines, you can already specify all the lines that are required in order and create directly the Gaussian input. So let's say that in this way you can create alternate scripts which run. Where you can move from PDBs to XYZ file really fast. So then what should we do? Since we have those atom types which look a bit weird, the thing that makes me think is that we can, for example, do the Antechamber and obtain our PDB file, our XYZ file, so that we remove all the weird things. So I do Antechamber -E, which is -input, then -FE, so is the input format, then -O, we call lig.com, since we will be using Gaussian. Now, also, if you don't have, if only with Amber tool is enough, you don't need to have Gaussian to create the file. And then lig dot, then the GCRT, which means Gaussian Cartesian coordinate. Then, okay, so this is enough. So now let's see, and we have obtained our lig.com file. Okay, now we see we removed all these weird atom types. So from this structure, we can go to now to a mol2 file, which is basically a file which also contains the bonding parameters and the charges. So let's do the same step again. Antechamber. This time as input we have the lig.com, and as input format we have the GCRT, Gaussian Cartesian. Now minus O lig.mol2 minus FO mol2. Then before I start, let's go back. Those are the charges method which you can use. So usually, in order to have a precise charge, you first do geometry optimization of your molecule, and then you do ESP charge calculation, and then you obtain those charge from a QM calculation, and you save them in your mol2 file. So, for example, you can already, from the Gaussian output, you can already call you can already use Antechamber to extract those charges without having to open the file and extract the charges. In this situation, in order to speed up things, and also because the purpose is not precision, we will be using this semi-empirical method for obtaining charges. Therefore, for the charge, let's see, for the charge is minus C. Where is it? Charge method. And then we will also be using the minus AT. So minus, which gives the atom type. So we will be using, for example, GAF. So it's the default, so we would actually need to write it. So what, let's see, it was BCC, I think. Yes, abbreviation, or you can use the number. So, okay. So now it's doing its small calculation. Okay. Now we have our lig.mol2 file, which is, as we see now, it generated the atom types as are recognized from our GAF force field, our general Amber force field, sorry, which are not those, but are those here. Then we have our XYZ, and here are the charges that are obtained from the calculation. Then now the residue name is automatically changed from LNR to mol. Therefore, either if we like the LNR, we change it manually. Otherwise, we keep mol, and therefore from now on, every time we need to call it with this residue name. So let's go down. For example, those are the bonds between our molecules. Okay, so this is our lig.mol2. Now,
Vito,
before, sorry?
Vito, there is a question for you.
Yes.
Why are we using Gaussian input files? Shouldn't we use Orca input file in the YouTube?
Yes, of course. So no, this was the purpose of this action was just to obtain an XYZ file, a mol2 file without those lig.pdb. Yeah, we will be using Orca, yes. But let's say to here are because the thing is, now I'll show you. If we do, for example, now we have this lig.mol2.pdb. Now the antechamber will generate the this mol2 file with those atom types. Those atom types in the next step for the solvation of our molecule, where in the solvation, let's say in the next step, we will be sourcing the force fields. And by sourcing the force field, we need the correct atom types. Therefore, I needed to find a way to quickly obtain the good atom types. And the easiest way was to go to an XYZ file and then go to a mol2 file. I didn't use Orca because, let's see, I think maybe there is also, so here you can recognize the Gaussian output. They still probably, no, they did not use the Orca XYZ. Also because the Orca XYZ is just an XYZ. Instead, the Gaussian has both the action part, which is the beginning, so this part, and then this part. Instead, in Orca, I believe that is the number of atoms here, then one line, and then this part. So more or less is the same, but don't worry, like it was just to use, it was just to obtain a file. It was not because I want to use Gaussian. Okay, so now the next step before we go to the solvation.
There is, sorry, Vito, there is another question. I
Yep.
copied it in the chat again.
Okay, wait. So how do you optimize the input, and why you choose GRT? So GRT. So no, how to optimize the input? So well, for example, now what I've done. My first action was, let's see, was to go from the PDB to the leak.com. So our Gaussian input. Therefore, I use the GCRT because this GCRT means Gaussian Cartesian coordinates. You can also use the Gaussian Z matrix, but I like the Cartesian coordinates. And therefore, yeah, then in order to optimize it, then you run your Gaussian calculation. Or if you have Orca, you get this file, and then you have also the input of Orca, and then you will run Orca as usual. So usually I do this thing of the electrostatic potential charges with the Gaussian. I've never performed it with Orca. I know more or less how to use Orca, but I'm not really tight on it. And so yeah, so this is why I chose GCRT for yeah, just for simplicity. Okay, so all right. So now, before we go on, before we continue, we need to obtain the final file, which is the FRC file, which is the last file we will require, which is the force field modification file, which contains, let's say, all the information which are not in the force field but are for the molecule, are required for the molecule. In order to do so, we need to use the next package, which is ParmCheck, which is from the Parmed. Then later on, I will probably show you in Amber where to find all these things in the Amber manual, where to find all these things, because I'm talking, but at the same time is also nice if you read more in depth about all these tiny panel of all these packages. But anyways, so the ParmCheck -H, let's see, just to be sure. Now we can input our file, we can output our FRC mode file. And then instead this time, I don't know, for some reason it's just -F, not -FE. So sometimes I make mistakes, and because in Antichamber it's -FE. Therefore I do parm chk2 -E lig.mol2 -F mol2 and -O lig.frc mode. Yes, 1 second. Okay, so this is, let's say, a remark. This is a file which contains possible modifications, and here it tells you, let's say, the penalty scores for these dihedrals, for example. If it's higher than a certain number that right now I don't remember, then you should find a different, you should change, you should basically change this dihedral, let's say, so change the number. Now, let's, so what we did until now. Let's go back. Now we have the protein, we obtained this amber.pdb. In the ligand, the final two files that we obtain are the lig.mol2 and the lig.frc mode. So what we do now is we copy from the protein. So what we have obtained the correct structure in order for the next step. So we copy the amber.pdb to let's go back. Now here I have the TLIP folder, so I will put it here. I will tell you now what is TLIP, because it's a weird name. I didn't tell you. I never talked about it. So we copy it, and now we copy the ligand, lig. Let's copy all the lig in TLIP again. And now we open our TLIP folder. Now in this TLIP folder, we have all those files that we just worked with. We actually will need only these two lig, but why not? And then now we open this TLIP. So TLIP is the next stage of Amber, which is a software that helps, no, it basically does the generation of the solvated complex. So, and how does it do it? Let's open the file. So this is an input file. Of course, you can also use TLIP directly from the terminal and provide each line by itself. But let's say that I've decided to create an input file and then directly run the TLIP. So here, first of all, what we do is we source the force fields. Therefore, for example, let's see this force field. Now let's locate. We do locate. Okay, so let's open it. Here we have all the atom types. It specifies this is the atom type. This is the atoms of for the force field, and this is if it's sp3, sp2. And then at the end of this file, then there is this gaf.dat file. Let's copy it. And this is a file containing all the parameterized different atoms. So this is, for example, the atom, the single atom itself. Then here we have for the bonding parameters, because we have only two atoms. Then go on and on. We will have also the angle parameters and the dihedrals. So yeah, if you're interested, you can both look at the Amber manual, but also those files, because I think it's also important to understand the architecture of the software itself. So now what do we do? Let's open again TLIP, sorry. So now how does TLIP work? We first source our files, our force fields, sorry. Then we need to define in a certain way our molecules. So TLIP work in a way of, we need to define a name, let's say. Then we have an action, and then we call the file that we will be using. So here we call molecule our lig.mol2. Then we load these extra parameters, and we save a library which contain both of those files. Then we call again the pro. For example, the protein, I call it pro, and we do pro equal load pdb, and then amber dot pdb, for example, which is the file that we used. And then there are many different actions that TLIP we will example, the combine, which combines those two files again. So we combine them, and we'll be generating the topology. Wait, sorry, my computer says the connection is unstable. Can you still hear me?
Yes,
Yes.
Yes, we can hear you.
Okay. No, just yeah. Okay, thank you. So, all right. So we combine those two molecules, and then here there is the second, another part, which is the solvation, which there are also other commands in this part, for example, adding the ions and so on, but I minimized the amount of commands to use. So here it says the solvate, which we could either use the solvate box command, which solvates in a cubic box, or solvate oct, which solvates in an octahedral box. So we tell him to solvate com, which is basically the combination of those two files, with what, which is basically the atom type name of the water, sourced from the force field of the water. This is the force field. So this is force field of the protein. This is for the organic molecule. So, and then we say save the Amber parameters of com of system.parm, which is the topology file. Now we will see them, and then the restart file, which is basically this is the coordinate file, and then we save again the system.pdb, which is the total system. All right. So let's run this command. Okay. So we do tlip -f tlip.in. Okay. Okay, so let's look at what happened. So it basically sourced the parameters. Wait, where are we? Okay, it sourced the parameters, then it read our molecules, it read the parameters, then it also added the missing atoms, because sometimes there are also missing atoms in the X-ray in the experimental structure. Then basically solvated the box. Then here in principle you should also add the ions, but I did not do it. And then it tells you we have this structure which goes from the terminal the C terminus of this of the residue to this one, with also our molecule and 12,000 residues. So in total it's quite a large structure, but I wanted to show you how to solvate a full protein with ligand and not only a ligand. So let's open the system.pdb. Now we have the full structure. If we want to search for our molecule, we do this. We take we see our molecule, and then we have all the different water molecules. One thing I forgot to say is that Amber renumbers this. So if we remember before, it was starting from 25, and now it starts from 1. So basically, I think, if I'm not mistaken, let's go 1 sec. I will go 1 second to the initial structure. Here there is the renom.txt file, which, at least if you get lost with your residue name and number, you can see which correspond to which. Okay. Okay, so then we generated also this system.parm7, which is our topology file, which comprehends basically all the information of the force field. It tells you the amount of total amount of atoms. This is, for example, 25, most probably is our ligand. This is the waters. This is the protein, probably without hydrogen, and this with hydrogen. And then this is a really long file. And then we have the system.rst, which is our coordinate file of for our simulation. At the end of this file, you can also find the periodic boundary condition. Sorry, the size of the box. Okay, so now we did the tlip. So we cleaned the structure. We created the files, and now we can begin to run our simulation. So we copy all the system files back into run. No, wait, run. Wait, let's go inside of run first, so I'll show you how it looks. So inside of run, I have I have minimization, heating, and production, and then I have an extra, which is the QMMM. So first we will do the minimization. So let's go to inside of min, and let's copy from the tlip file all the system that we have created, and we copy them here. Now,
sorry, Vito, there is another question in the YouTube channel. So wait,
yes.
I'm gonna copy and paste it.
Okay, 1 second. Okay. Yeah, this is a good question. How to retain the residue number, or again renumber it. So since, let me think. Yeah, it's a bit annoying, because I believe that also in the system.parm7, which is the topology file, it will be written from starting from 1. So I don't think that there is a way to actually go back to rewrite it with the, maybe there is some options of TLEAP. I actually don't know. This one, no, I don't know how to get back to this one. So this is why it also said to keep in mind, because also, for example, now before we start our simulation, let's see the structure. So Arthur, I think that if you look again at your structure, so there is a question: did anyone else got the following error? Most probably this DMU was in the initial structure here. When you got you did not in the chain.pdb. No, sorry, wait, where was it? In the first, yeah, in the chain.pdb, this one, which was the one containing also all the residues. Probably you did not cancel the DMU, which was another organic molecule. I think it was one of the lipids. Can you check again? So yeah, okay. So the thing is, so what you should do is again those steps. So redo this, reduce and everything, or just in case if it did, try to just remove it from the final step, from the amber.pdb. So from this one, from the last one, try to remove this DMU. Okay, and then you can run the TLEAP again. And so in principle, if we would have kept the ligand nomenclature as this, we would have encountered the same mistake as Arthur found, which was that this kind of molecule does not have an atom type, because those atom type are not recognized. So this is why I wanted to do to pass through XYZ file. Now, okay. Now let's go to again to run minimization, but before we open it, before we start the minimization, let's observe the system. So in this case, you can either do this and open the PDB, or let's do it directly from VMD, so that you learn. So here you have to load the parameter file. Now, I think I made a little mistake, because this is not actually a restart file, but is a coordinate file with periodic box. Therefore, we should select this and let's see. No, it's not working. Therefore, let's see. Delete molecule. Let's see if we only open this. What happens? Okay, no, it works with the periodic, with the restart. Okay, so this is our structure. Very, very beautiful. So this is the our octahedral. Inside we have our protein. So again, here in representation, if we want, we can do protein, and we have our protein itself only. Okay. Then we do now again. Now rest name will not be LNR anymore, but will be mol. And let's get it in. No, okay. Oh, sorry, we didn't rest name mol. Okay, so this is our structure. And then we do the water. Okay. Anyways, yeah, you can find many ways to visualize it. Here you can also change for example, the background. There is many things you can do also for visualization itself. But I think if you want, we can continue. And so let's close it. Okay. So first of all, now we have our structure. The first thing, so what is going on now is that we have our structure, but it's not minimized. So most probably in a potential energy surface is in a point close to a minimum, but not in the global or local minimum for this structure. Therefore, the first stage is to minimize the full structure. And now this is the minimal input file that you have for the minimization, because I did not include many other keywords. So first of all, how does this work? So first we need a line called, I called it minimization, but you can call it as you want. Then this is the control part, which goes from here to here. I believe that this can either be here or here. It doesn't really matter that there is a space here. And also here, there doesn't matter if you have it a space or not. But it's important that you have this line and this line here, and this one in general. So now what are the options that I've specified? So E_min equal 1 means turn on the minimization. So for the other stages, for example, will be equal to 0, which means we're not minimizing the structure, we're actually doing molecular dynamics. Then we do, this is the Mach cycle of, which means that for the minimization, we will do 200 steps, of which, of these 200 steps, which is the total amount, the last 100, we will switch to a more sophisticated algorithm, okay? And then those two inputs are telling us. NTPR means print energies, which is the output file, and it says print it every 2 steps. And this is print the binary file. So print a file containing the information about the coordinates. Okay, so now let's close it. And how do we run this calculation? Now we've used, for now we used all these PDB for Amber, we use the parm check, sorry, the antechamber, this parm check, this TLIP. Now this other software that we will be using is the one that I tested before, which is Sander. Sander is responsible for running molecular dynamic simulations. Now, what is the nomenclature? Let's do Sander -H. So we require the MDIN, which is the input file, which is our minimization.in. Now we specify so we specify the output file. Then it requires our topology file, which is a PRM top, but in this case I called it parm7. Then we have the -C, which is the input coordinate. The -R prints the restart file, which is basically the last file, the last frame of our simulation. Therefore, so that we can start a new simulation from that frame instead of restarting from 0. And then then there are many other options, but those are the most fundamental. Usually also add the -inf, and then also the -x, which is the full coordinate. So here it prints only the restart file, so the last frame. Instead with -x, it prints the full coordinate. Okay. Therefore, we do Sander -O, which -O large is here, means basically you can overwrite all the files. So imagine that we run the calculation and it's wrong. Then if we don't put this -O, if we run another calculation in this folder, if we don't put this -O, then it will not start the calculation because you did not tell him to overwrite those files. So let's put it always -O -E min.in, then -P system.parm7 -C system.rst7, then we have -R, and let's call it min.rst7, and then -inf min.info. Then we put, for example, this in order to run in background, and let's run the calculation. So until now, are you all following? Or at least the people in Zoom, are you following, and are you in the same stage? Okay. I guess it's a yes. So okay, so for example, here I made a mistake, but because if we go again to Sander, I did not put the minus O. So in this case, if you don't put the minus O, it will output the output in a file called mdout. So let's move this file called mdout to be consistent. Let's call min.out. Okay. So next time for the heating, I will run the minimization. Sorry, the heating with the minus O. So let's open the minimization. So here, so it's not many steps because I've only performed 200 steps. Therefore, we reached a point close to a minimum, but most probably will not really be at the minimum. So, but we see that the energy is decreasing. So here we see it. I will plot later on for the heating. So if we go until the end, we see that the energy has reached a lower point. Those are the bonding, the van der Waals, and the one for van der Waals, the dihedral, the angle, the electrostatic, and the one for electrostatic interactions. So let's say that we can use this structure for the minimization, for the heating, for the next step. So now,
sorry, Vito. There was a question on the YouTube channel. I'm not sure whether you have already answered it or not. I was off for a second.
okay.
I'm copying it.
So so I will read it. Choosing the solvation box might also influence the simulation. So let's say that depends, I think, on the structure of your league, of the things that you want to put inside of the solvation. So for example, I usually work with the transmember proteins, which are inside of a membrane. Therefore, if we imagine the structure of a membrane where the water should be on top and below, let's say that for example, an octahedral box is not really the best one, but we should use a rectangular or a cubic box, let's say. Say that I use the octahedral because if you only simulate, for example, one ligand or a protein ligand system, let's say that the octahedral minimizes the amount of atoms. Let's say that the less atoms we have, and the faster is the calculation. Also, if we go again to the tlip .in, I did not tell you, sorry. This is the length from one of the last atoms of our system to the end of the box in Armstrongs. So in principle, the cutoff should be low. The cutoff of our simulation in the heating and the production run should be lower than this number, because otherwise you would have interactions between different boxes. Then, okay, Gustavo, if you have any other ways to answer this question, please do.
No, I think the main reason is for, of course, as you said, depending on the system you're dealing with and the computational efficiency you want to also to attain. There is yet another question on the YouTube channel. Yeah, Juanjo has just copied it on the chat.
Okay, so can you comment on difference between steep descent and conjugate gradient for minimization? So there are two different algorithms. Personally, I cannot really give you a deep answer about this. So I can, let's say, tell you, let's say, where to find these informations, but right now, like, I cannot really tell you the difference between the algorithms itself. So yeah, if Gustavo or Juanco, you have if you can answer this question.
Yes, I can say something. So usually, let's say in conjugate gradient, when you move from one geometry to the other, this movement is larger than in step descended. Let's say when you are very far from the minimum, you want to do large steps because you are still far, so you need to, let's say, move let's say larger, and for this you use a conjugate gradient. But then when you are close to the minimum, you need to already refine a bit the search, so you need to do smaller steps. So the steps are less linear, so they introduce curvature. So let's say the difference between one geometry to the other doesn't depend only on the gradient, but also on the Hessian, on the second derivative of the potential energy with respect to the gradient. So this is the main difference. So indeed, if you Google, this is a typical question. If you Google a steep descendant versus conjugate gradient, you will see a lot of figures where they explain it in a graphical way. Okay, so that's the main difference. I don't know if Gustavo wants to add something.
No, I personally don't know in detail the details of the conjugate gradient algorithm. So yeah.
So give me just 1 minute, Vito. Let me.
Yes.
Just 1 second. I will share my screen. 1 second.
Would you? Yeah, we'll stop my sharing then, or. Oh no. Okay. Perfect.
Yeah, you don't need to stop. So okay, here you see my screen, right?
Yes.
So that's let's say this is in a general way, but here on the right you see the conjugate gradient, where as you see the variation, let's say the search is more linear. Let's say when you search in the phase space. So this is the first geometry. This is the second one. So you move in a linear way, and the step is very large usually. But when you are in the steepest descending, it's good when you are close to the minimum because you can move in a more zigzag way, let's say. So you introduce curvature in the algorithm. So that's the main difference. Okay, in a graphical way, let's say. Okay, so I think you need to share again, I guess.
Yes. Okay. Wait. Okay. Share entire screen. Allow. Yes. I see myself.
Perfect.
Okay. So we finished our minimization. So in order to continue, let's see where I am. Okay. So what we want to do now is to take the files that we have generated, therefore the min.rst7, which means restart file, and we copy it to our eating folder. Okay, so now the topology, of course, stays the same. So we need this system.farm7 in all the folders from now on. Therefore, we also copy this in the eating folder. Now, let's do the eating and let's see the input file. So the eating is a little bit more complicated. So first of all, for example, let's say here, as I said before, we turn off the minimization. Then those two NTX means that we're taking from a restart file, but we're not taking the velocities, we're only taking the coordinates. If it was, for example, NTX equal 5, it was telling you also let's take the velocities, for example. So here we'll only take the geometry from the restart file. And then, for example, this is the number of steps that we will be performing. Then this is the time step, which in this case is 2 femtoseconds. So let's say that the time step for molecular dynamics simulations is it's around 2 femtoseconds, because thanks to the shake approximation, basically we can, which basically avoids the vibration of the CH bond and approximates it. It constrains all the bonds involving hydrogens. We can increase the time step to 2 femtoseconds. Otherwise, we would require to have it between 0.5 femtoseconds and 1 femtoseconds. How do you get this number? Let's say, if you have, for example, I don't know, if you remember in spectroscopy, in IR spectroscopy, usually I don't know, we work with wave numbers, but if I remember correctly, the wave number of the OH bond, for example, or the CH bond was around, no, the OH bond was around 3,600 wave number. Okay, a wave number is equal to 1 over lambda. Therefore, for example, if we do the energy, which is equal to HV, where V is the frequency, HV is equal to HC over lambda, which is also equal to HC wave number. Now, if we equalize HC wave number to basically the seconds, because that's what we want to obtain, so we would have HC wave number equal to H over seconds, because the frequency 1 over seconds. Now, if we cancel out the two Planck constants, then we would have C wave number equal 1 over seconds. So seconds is equal to 1 over speed of light multiplied by wave number. The wave number usually is in centimeters to the -1. So if you do this calculation, most probably you will reach a number which is in the femtosecond scale. Then we have our initial temperature, our final temperature, in which we want to reach with our thermostat. Then here again we specify the printing of the energies, and we specify the printing of the coordinates. Then here we specify that we want to print them in these not in binary files. Then now we have the cutoff. Then the EVRAP, let's say that it works in a way that wraps it brings all the coordinates in its usual periodic boundary condition. So let's see if we will be working. Otherwise, with some post-processing tools, we can also put it back into for visualization inside of the correct box. Then here we turn on we still don't have a pressure control, but we have a temperature control with this thermostat. And then here, for example, we have a final part where we specify, this is the keyword in order to specify the last part, in which we say we are telling from step 0 to step 2000, please go from 0 to 300 Kelvin. Then from step 2000 to 3000, let's keep this temperature. Now, most probably, since the system is quite large, I think that this final part will only works like for such a large system. We would need to specify a larger amount of steps. So let's see if it works, and then we will observe. We will plot the temperature and the total energy, and also other kind of energies. So now we do again the sunder. So we do sunder minus O minus E E dot in minus P system dot param7 minus C min dot RST minus R EAT dot RST7 minus X it.crd, which is coordinate file, which will contain, as I said before, the full path, the full simulation. And then what am I missing? Always it.out, and then minus inf it.info. So I think there is everything. So I've submitted the calculation. I think I've tested this calculation before, and it will take around 10 minutes. So it will be the, let's say, the longest one, because the production run before the next step will be probably 3-4 minutes. Therefore, if you guys want, we can have a quick break now. Otherwise, I can tell you other things. I can answer a question, whatever you prefer. Okay. Wait, because I don't know. Let's see the chat.
Yes, probably if you want, Vito, you can do a break of 5 minutes. Maybe
Yeah.
today we can have 2 shorter breaks, maybe.
Yeah, because let's see, most probably, wait, no, let's see, because in the it.info, in principle, it will tell you the estimate time remaining. So we have 9.9 minutes. Okay, but yeah, we can also take a 5 minutes break and then slowly come back. Okay.
Okay.
Great. So see you soon.
Yeah.
Okay.
Okay.
Thank you.
So 5 minutes of break if you want. Okay.
Hello? So I see a question. Okay, fatal error, could not open file lip RC protein. So did you solve it? What? So I see, wait, okay. Let's go again to TLIP. So we see, wait, okay, I'll wait. So the person who asked the question, why Wagner, first of all, are you listening? Otherwise, I'll wait. Okay, let's go back to TLIP. Now it's, so are you in my computer? No, you're in the other computer. Gustavo, are you there?
Yes, I'm here. I've just changed PCs with Juanjo. So, so you're in the other one?
Okay, yeah. So in principle, check if first of all the permission, but in principle, the permission should be of tutorial, so it should be of everyone.
Could it also be a problem of the Amber version? Perhaps that force field is saved with a different name on the Amber 18 version?
Okay, yeah, but
no, I'm asking.
No, it could be, but in that case, then everyone should have had the same error. So I don't know if.
Has anybody else had the same error in the other PC?
Okay, see, yeah, Aline, you're in my group. So the thing is, Gustavo, you have Amber 18, right, in your computer?
Yeah.
Okay.
Just
yeah. The thing is, in my computer, I have Amber 20, and he has Amber 18. But in principle, they should have the same nomenclature. In case, Wagner, can you try to do the locate and then liprc protein and see if it actually exists? So I'll do so like this. Let's say, wait, let's go to the tlip. So tlip.in. So this one, because we're sourcing this force field from a folder. So try to do the locate and then this one. Let's see if it actually exists.
No, it doesn't find it. So I guess it is present with a different name.
Okay.
I think in the case of Amber 18, we should use a different version of that force field.
Okay.
So where is it? So in that lips.
CMD, yes, yeah. So in principle, then we can use the 14. Gustavo, which one do you use for proteins then?
Yeah, the FF14SB could work just fine.
Okay. So I'm really sorry. I didn't know that that was not existing in that computer.
Yeah, my PC is outdated. I am sorry.
So let's go back to tutorial. So in principle, also for all the others did not work. So what you should do at this point, sorry, hello? No, okay, nothing. No, Vito, tlip. In principle, you should change this FF19 to 14. Okay. And try, let me know if it works. Yeah, don't worry. It takes time. And then we can continue, but we have a lot of time. So. Okay, it's working. Great. Then now, yeah, you have the PDF, but please, then you have the system.parm7 and RST7. If you want to wait, let's go to the minimization so that you're on track. So first of all, now you are in this stage. So copy all the systems dot whatever to the run min. You copy them here, and then go to the folder and do the sander. Wait, is this one? Yes, this point. Let's add the -o min dot out. Okay, and you should run this command. Okay, no, but yeah, I will continue, but please then run this command. When this is done, I don't know if you saw, then when this is done, then copy the min.rst7, the system.parm7 in the eating, and then perform the same calculation, the same command, but with the eating. You have it in the PDF. Okay. All right, so let's go back. So now we see it.info. Now in principle, it's done. We see this is, so this is the final step. This is the amount in picoseconds. This is the temperature that we reach, or at least the temperature of the final step. So what we can do now is we open this it.out. First of all, are you all there? Can I continue? Antonio, are you there? And
Yes, I think so.
okay, yeah, I guess. Okay, great. So yeah, let's open the it.out. So, and now we see, I will plot it, but let's say, yeah. So what we should see, what we should do is, for example, we should plot the temperature, and also we plot the total energy, for example. So let's do it. Unfortunately, you can either do it by extracting the file, the column, or you can use this process.mdout.perl, which is a Perl script, which is already number tools. Okay, so which you provide the output name, and automatically it outputs all the summary of all those observables. So in this case, let's see, for example, we do it with xmgrace. 1 second. Okay, xmgrace, and then we do summary, for example, .temp. So most probably, since we were turning on the thermostat, as soon as we turn it on, let's say that reached this temperature, then slowly went to a lower temperature, and at this stage it started eating up the system. So let's say that I've tested this calculation, and I found that at 3,000 steps was where more or less we were reaching it. Then of course you should always run a bit more time once you reach the temperature. But at least now we are more or less in a frame of having our simulation at the correct temperature. So then from this, then in principle, also the energy should reach a constant value. So we also plot the xmgrace summary of etot. Let's see how it's called. Etot. And so let's say that this is at the end of the 6 picoseconds, we have more or less where we're reaching a constant temperature. So now, okay, we have eaten the system. Now we need to turn from an MVT ensemble to an MPT ensemble. So we also need to now add the barostat to our simulation. and run the production, so the final stage. Usually in MD simulations, there is the minimization, then the heating, which is this part, then there is an equilibration, where you reach the final temperature, with a constant temperature, reach the correct pressure or density. And so in this equilibration, let's say, is the same. They're the same settings are the final run, which is from where we actually will extract the data and the things that we want to analyze. But the first, let's say, I don't know how many, but some steps should be discarded from the simulation, and this is the equilibration part, where we reach the correct density and then we run the simulation. In this situation, since, let's say, the purpose was only to actually run the production, I've run a really short production in such a way that then now we will use those data to then extract the correct information. So what we do now is, first of all, we copy from the heating, the heat.rst7 again here. And then we copy the system.parm7 again. Okay. Now, finally, we do the sunder minus O minus E prod.in. No, wait, let's open the prod.in before we run it. So now what changed is that now we have this NTB, which is in the now equal to 2, which means that we're in the MPT ensemble. Then we have this NTX, which before was 1, and rest equals 0, which means that now we're both reading the coordinates and also the velocities. So our restart file will actually probably have 2 steps, because we'll read also the velocities and the box informations. And then those are really similar to previously, but we also have the barostat on. And this is the pressure in bar, and those are other input files for the volume, for example. And so now, for example, here I've run only 1,000 steps, because I believe that for now, let's say, I want to show you then how to extract the information with the CPP trajectory, the post-processing file software. And so those are then the output instead as before. So we will print every 10 steps, the energies. We will have a restart file every 20 steps. Sorry, no, the energy every 1, the trajectory every 10 steps, and the restart every 20. And those numbers, of course, you change them depending also on the amount of steps, because this is, for example, I believe this is 2 picoseconds. But if you're running 200 nanoseconds, then I highly suggest to not print every 1 frame, because otherwise you will have a file of 100 gigabytes. So yes. So then again, we do sunder minus O minus E prod.in minus P system.parm7 minus C. Yes, minus C heat.rst minus R prod.rst7 minus X prod.crd and minus O prod.out minus inf prod.inf. Now we are running the simulation. Most probably this will take 4 minutes. Let's see. Here we go. So 4 minutes. So I think that in the meantime, in these 4 minutes, I can already introduce you to the next stage, which is understanding how the post-processing software works, which is incredible because you can do infinite actions. So first of all, the command is CPP trajectory, which you can either do the CPP trajectory minus E and then the file. So you create actually a file.in, or just CPP trajectory and then you work interactively. Okay, please let me know if it's working also for you. In principle, it should work. But yes, so this is the CPP trajectory analysis. I will do it interactively so that we can understand more or less how it works. So here, for example, the meantime that the simulation is working, I will introduce you to what are the possible things that we can extract, for example, from the system, from the topology. So you can extract all the information from the topology, and I will introduce you to the atom mask or distance mask. So let's do CPP trajectory and let's enter. First of all, the nomenclature work command, then name, and so on. So we do parm.system, so dot parm7. For some reasons it's not working, the tab is not working, but anyways it's okay, so we will write properly. So parm.7, so in this case then the parm is the action. Will be alone now for 20 minutes because we got a meeting. Okay, all right, no problem. Yes, so let's execute this command. So it's telling you basically that it's reading the topology. Those are warnings, but don't worry about this part. And now, okay, so let's think how I can introduce it. So in order to introduce you to the atom mask selection, I believe that, for example, we can use one action, which is, for example, charge, which is, if you write only charge, it will tell you the charge of the total system, for example, okay? So we will use charge as an example of an action to do. Therefore, there are two ways in which you can, there are many ways in which you can extract informations. So there is the atom index nomenclature, which is with this, with the at, or the residue nomenclature, which is with the double dot, like this. So for example, charge, let's do charge of atom index from 1 to 100. This will tell you the charge sum of the charges of atoms from 1 to 100. Now, if we do, for example, charge double dot, if it's called double dot, from 1 to 100, now in this case, what will happen? It will take the sum of the charge of residues 1 to 100. Okay. So then let's see what else, what other ones I can do. Okay. So if we remember our PDB, we have the atom index, we have our residue index, but we can also have, also residue number and atom type or atom number, atom type. So for example, we can do charge of, we want to know the charge of all the alpha carbons, for example. All right. So now, again, let's say we want the charge of only the asp, of only this residue. So in this case, it will take, before it will take all the alpha carbons of all the protein, but in this case, it will tell you the charge of all those residues, okay? Then what else? So those are the main ones. Then there is many others. So because you can also combine. So for example, we want to know only the charge of asp, so double dot asp alpha carbons, which means we want to know only the of alpha carbons. So this is, for example, to combine the residue name and the residue name and the atom name. Then you can also use, for example, there is also other nomenclature, which is the and, then there is the or, and there is the not. Okay. So, for example, we say we want the charge excluding all the alpha carbons, the carbons, the carbonyl carbons, the oxygens, the nitrogens, and the hydrogens. For example, this is just random. So it will tell you the charge of all those, of everything that is not this, okay? Now, why am I telling you all this? Because now I'm just working with the charge itself, but we will be able to extract all the possible informations from our trajectory with this nomenclature, okay? So now those are the basics for the atom mask. There is many other ways to select different things, but I believe that for now, then I think that the only way to actually learn it properly is to go to the manual and look at all the possibilities. So, but at least you need a basic structure of how the overall structure of all the how the overall structure works. Then we have the atom mask, and then we have the distance mask selection. Okay, the distance mask works of so outside of a mask or inside of a mask. Therefore, for example, we want the charge again. We write again from 1 to 100 of residues. Lower, so this is within for example, this one tells you atoms which are 3.0 Armstrong. So this will tell you the charge of all the atoms around these residues. Okay. Now what I see is no reference set. This is because for the distance mask you need to add a reference. So in this situation, of course, we don't have we're working only with the topology, so we don't have coordinates, so it's pointless to use the distance mask without coordinates. So then at this point I think that the simulation ended, and we will continue doing this with the simulation itself. So let's close. The simulation is actually done. We have the prod.out. The simulation finished. Please stop me if you have any questions. And so let's do again the process.mdout, prod.out. Always do it just to have. Now in this situation, for example, we did not. So let's open the prod.out. The best way to see if in this case it reached a correct density to reach is to actually check this number here. So in this case, the density of this system should be reaching 1, which is more or less the density of water. And with also in a water system, let's say that it depends mostly on the solvent, because it's the most amount of atoms that we have. So when this number will reach 1, we can define the system as equilibrated. If we go until the end, we see that actually the system did not reach at all the correct density. Therefore, this is still, we are still in the equilibration part. But for the purpose of this simulation was just to, as I told you 10 times, is for the purpose of actually reaching the end and finding and showing this is in principle how you should run a calculation. Now, let's go back at this point to the CPP trajectory. So first of all, let's open in VMD. So actually, let's do it like this. VMD. Okay, then file, new molecule. We browse our system. .parp7. And then we browse our prod.crd with periodic box. So if we see this does not look great at all, this is because actually the imaging of the production run, the keyword that I told you before, ebrap equal 1, I believe that only works for cubic, because it did not do what it should have done. Therefore, let's say that in this situation, this is a good way where we can use a CPP trajectory. Okay, so let's close BMD again, and let's do CPP trajectory. you can either do also system.parm7 right directly here, but we do, since we want to learn all the keywords, we do directly cpp trajectory, and we call it parm .system.parm7. Okay. Now we want to load on top of this topology, we want to load the trajectory. This can be done by do traj in, then the name of the trajectory, which is prod.crd coordinate. Now this trajectory, okay, no, I will tell you later on about the other possibilities of this, but let's load the full trajectory. Okay, so it's reading the trajectory as Amber trajectory. Then now there is a action which is auto image, which is basically an automatic way which CPP track has to image your simulation inside of the primary box, and therefore be able to visualize it properly in BMD. Now for the keyword, I think for octahedral is familiar. Let's try if it works. Let's check if it works. So auto image familiar, and then we do traj out prod, we call it prod image.crd, for example. Okay. Now, in order to execute all those, you have to always write go, because before I showed you all the possibilities that we had for the atom masks, but we never saved actually the files. So later on, now I will show you how to also save all those information that we called with the actions. So we do go. Now it's basically saving the coordinate. We do exit, and now we open again BMD. System.parm7. Prod image. Okay, now it actually worked. So we see that the system has inside of the octahedral, and again, now unfortunately, since it's a small simulation, I cannot really show you many things, but one analysis that is usually done with protein systems, and also to see whether the ligand actually stayed in the position in this binding pocket, is you have the trajectory tool of VMD. Let's see, let's have it here. For some reason, recently, this trajectory tool is slow. Okay, so first of all, we want to align the protein, which means let's remove all the rotational and translational motion of the protein. Therefore, so that we can actually analyze the root mean square deviation of our protein, only we're removing those motion, and therefore only movement of with itself. So with the first frame of our simulation. So we align the protein, and now we plot the root mean square deviation. Let's see. Now, since the system was not actually equilibrated, of course, we see that it did not reach a convergence. In principle, after a while, it should look like more or less a line that oscillates, fluctuates within a point. But this did not happen because the system is still not equilibrated. Then you can also do the RMSD of your rest name mol. I hope you see because it's quite small. And we can plot the root mean square deviation of the protein, of the ligand in comparison to our protein, to my protein. And now, as before, since it's not equilibrated, we cannot really judge, but there is a root mean square deviation of basically maximum, it goes to a maximum of 0.9. Therefore, now if we keep this here small, we actually do the protein, and we new cartoon. Let's do here, I like to put orthographic and a bit more bright. And then we do res name mol, sorry, not lig, licorice, oops, res name mol. So we see now there is really almost, so let's see where is the biggest fluctuation. Now this is in principle not really important because it's not a good system, but let's say at half simulation is where actually there is the largest fluctuation compared to the first frame. So here we see a small translation around this part, and then always starting to oscillate between a normal point. Now, in principle, the VMD also offers the possibility of a distance mask as well. So we do, for example, within 5, we say within 5 of res name mol. So print me everything within 5 Armstrong of res name mol, so that at least you see what are the residues which are fundamental for the ligand to be there. So now we cannot really judge again, but we see that, for example, there may be an ion pi interaction here, or for example, I don't know, there could be a hydrophobic interaction or a pi stacking. There is many, but this is just something that we can with VMD do it visually, but then we need to also do free energy calculations, or then either go to QM calculation in order to understand what are actually the interaction. But this is just something that I wanted to show you. Now let's please close VMD at this point. We exited, we did everything, yes. In case we open it again, okay. So now then we have our imaged trajectory. Let's go again to CPP trajectory. So farm system.farm7 rush in. First of all, maybe I believe it's nice to show you still without having adding any action commands, but only working with the trajectory. What are the possibilities, and how we can apply our atom masks? For example, we do traj in prod. Let's skip the image already since we did it. Image.crd. Then the CPP trajectory has a start, stop, and step idea. Therefore, you can say, okay, of this trajectory, since I printed 50,000 frames, I want to only have from 1 to 100, because in our case it's from 100 the maximum, every 2. So in this case, it will take equidistantly 50 frames. Okay. Now we say, okay, no, but I don't want the water. Therefore, I can strip, for example, all the atoms called water. So let's strip the water. And then we do traj out, for example, prod 50 frame, no water, dot. Now, here, what we can do now with CPP trajectory is also, we can output a really large amount of the different files. So here I can either output the coordinate file, but I can also output it. I think I wrote it in the PDB somewhere. Sorry, in the PDF, not PDB. The PDF somewhere. What are the output possibilities? In any case, you will find all these informations in the manual, which is only by itself is a software, because it's a really crazy amount of things you can do. So the trajin accepts Amber trajectory, Amber binary, Amber restart file, also charm trajectories, charm coordinate file, and charm restart file. Then it accepts the PDB, Mol2, and also Gromax in Tinker and Desmond files. this is the input, then output. Probably some of those can only be inputted but not outputted. Otherwise, we would be able to create coordinates of or topologies of other force fields, for example, of the charm. But we don't actually have it in number, I believe. But I don't want to. Okay. Anyways, so we do the trudge out, and let's save it as a PDB, for example. PDB, then usually it recognizes it if you put the .pdb, but just to be sure, you can put the PDB here, so you specify which kind of extension you want and what kind of file you want. So it's telling you writing it as PDB. So you do go. So go
for you.
Sorry?
There is a question for you from the
Yes.
people in the YouTube channel.
Yes, thank you, because please tell me, because I'm like, I cannot also watch YouTube because it's too much, and now Gustavo and Juanco are not here. So yeah, thank you. Did you copy pasted the?
Yes. The last one from Mauricio.
Okay. So okay. So I don't understand one thing. The position of the ligand on the protein is given by PDB file by the Amber calculation. So let's say that in this situation, I've taken a bound structure from the PDB database, which is basically a structure where the crystallized structure was already at the ligand bound to the structure. So that's actually the true binding pocket. But many times, like, you have an unbound structure crystallized, and you would like to find binding pockets of the PDB. Oh, sorry, binding pockets of the protein. I have this PDB. And in this situation, so the ligand, so the position of the ligand on the protein, is given by the PDB, because that's our starting structure. But then throughout the Amber calculation, let's say that we have sampled our phase space. And in principle, let's say that now with this really short simulation, let's imagine that this was a comfortable position for the ligand in its binding pocket, and therefore it was trapped there. Now, if we run for an infinite amount of time, most probably it will jump out of this binding pocket and also find other local minima, and therefore find also other allosteric binding pockets, which is also something that then you actually do in order to find the binding pockets of your ligand. Usually this is done also with docking, which is not based on force field, but other simple or simpler, let's say, equations, which are able to make you find the binding pockets, estimates of the binding pockets and binding free energy of the ligands with the protein. So but in this case, yeah, the protein, the ligand is given by the PDB, and then throughout the calculation was kept in that position. Okay, I don't know, I hope you understood. It's not that I didn't really answer, but yeah. All right, so okay, so now what we did here was to, let's see the summary of the process that we have performed. So we said, let's take okay, read 50 of 100 files from 1 to 100 every 2. Then we strip the water, and then we output it as PDB. So in this case, we can directly open the PDB in Amber in VMD, because we basically printed it as PDB. So let's open this file. And so here, basically, we will have our protein in 50 different steps. So let's search for mole. So therefore, this is the first, and model tells you this is the first stage, the first frame. Then starts model 2, and so on and so on. So if we keep searching for mole, basically we will have all the different models until 50. So if we open it now in VMD, yeah, okay, no, let's do it like from here. Why? So in principle, you can directly output VMD. You can already give the name to VMD, but sometimes it's not recognized. So it's better to do it here. This is what VMD does because it already automatically recognizes it. So here we have the PDB of our structure in the 50 frames with the stripped water already. Okay. Now, what else? What can I tell you about the CPP trajectory? This is, let's say, this was a way to handle, let's say, the trajectory. Then let's see. Now we can go to the action commands. Let's go back to what we were doing before. So system.parm7. No. System.parm7. Again, the charge. We do the charge of 1 to 100. And now, though, so it will give you, it will tell you this information. So this is the last info, the log file, let's say. But if we want the output file of this calculation, most probably, I hope it will be like this. So you need to tell them out. So output me this this in charge 1 to 100 dot res dot dot, for example. Now, if we perform go, let's see what happened. How do they call it? Charge. Yeah, charge. Okay, no, it will actually printed only the okay, printed this information. Therefore, I think there was a different way to, but anyways, we will do it on the trajectory itself. So again, let's do parm system.parm7. Now we insert our trajectory as no, now I remember charge. I remember there was a different commands, but right now I have to go to the CPP trajectory manual in order to. 1 second. Let's see if. Yeah, info. I remember was okay. Yeah, no. For the charge, I actually do not remember what it was. But for example, let's redo it. So CPP trajectory parm system.parm7. Now we want the dihedral info of mol, and we want to output it to dihedral mol dot dot. So this gives me all the information. Now I think I'm sure there is one also for charge. So in principle, for the charge is also nice because then you can get your point charge of any frame in such a way quickly. And if you want to do calculations, but there is also many other ways to do it, but this is one of those. So now CPP trajectory again. Let's open the parm system parm7. Let's input the trajectory, which is was prod imaged.crd. Yes. Okay, now there is many different actions we can do. Let's see, for example, the one that I've written in the tutorial so that we're consistent. For example, let's do distance. Yeah, do this, bro. Do distance and angle. So we do say distance. Now, for each of those actions, we can actually then give the atom mask. So we want the distance between. I believe that in the tutorial I've written, in the PDF I've written the distance between two atoms of of our ligand. Distance dot mol dot dot. Okay. So
There's a missing n.
Yeah, there is, wait, distance between 800, 84, 87, 84, 88.
I'm sorry, Victor, but I think there is still an n missing in the distance.
What? Oh my God. Nice, thank you. Okay, yeah, no, because I will, come on, it should work. Okay, thank you very much. So, okay, so in principle now the command, yeah, the spelling is important. Distance mol dot, thank you. Okay, now it's working. So it's giving the distance between those two atoms. In this case, the center of mass of those two atoms, but yeah, for atomistic, this is the center of the atom. So we go, and what it's doing now is printing, for example, distance mol dot. So it's printing me the distance between those atoms throughout the full simulation. This you can do with really a lot of different things. So for example, you can do also angle with in the same manner. Of course, in angle, you need to specify 3 out parm 7 in prod image.crd. Now we do, for example, angle. Let's see, what did I do in the tutorial? This time I spelled it. We do 8494 and 95 out angle. Now, in the same time, you can also output many different actions. So it's not that you have to do it one by one. So let's do, for example, let's get this. And hopefully, if those atom types are, you should always check before writing, for example, the atom types, what they correspond to. Now I'm just writing random number just to show you the idea. So dihedral, maybe did I call it already like this? Let's do triangle dot. Okay. And now if we do go, of course in the dihedral, for example, here is tell me output, the range is from -180 to 180. So there is, I think, one keyword.
The last number is wrong.
It's the same. Yeah. Therefore, perfect, because so I can also, yes, it's the same. Yeah. Thank you. Trial 2 dot. Okay. And then I think before writing out, I think there is one keyword which is one range 360, which, for example, instead of going from -180 to 180, we go to from 0 to 360. But yeah. Small trial. Thank you for telling me, because yeah. Now if we go, is performing all those actions. Now you can test really and open the CPP trajectory manual and test, because you can also do many things. Now I will show you other useful things. So this is, for example, the dihedral. Now, if we do, for example, traj in, for example, let's suppose you lost your mol2 file of your ligand. For example, you can do still traj in. Wait, let's open the system dot the PDB file. Let's see what PDB we had. I will show you one little thing. So let's go to mol, for example. So 8486. Okay, so this is the final number of the for the protein. Okay. We do traj prod image.crd. Now strip water, but we can also, for example, strip many different things. So from we say from 1, 2, 4, 8. Do you remember what was the 86? I think 8486. I think it was this. Anyways, this was a way to. I want to show you that you can strip different things, and then, for example, you can do trudge out lig.mol2. Now, I didn't do. No, actually, let's start again. Trudge in prod image.crd, and let's do, for example, from 1 to 1 to 1, which means let's take from the frame 1 to frame 1 every 1. So it will take 1 frame. And then we strip the water, and we strip the 8486. Now I'm doing it in this way, but you could also have done, I just thought about it, you can say strip, you can use the not, so the symbol that we've seen before, which corresponds to the not, in order to strip everything which is not something. Okay, so now I will show you also. So we do trudge out lig.mol2, mol2, go. And this is our mol2 file. Okay. Now, I believe that this is just a little part of what this CPP trajectory offers, but at least I've introduced you to the idea of how to load the trajectory and load the topology file, load the trajectory on top of the topology file, and then work with all the possible actions. I think in the PDF I put a link of regarding the CPP trajectory manual. Therefore, check it out because it's really really well done. And now, so what do you guys want to do? My idea was just now to show you how to prepare a QMMM calculation, so that for next time that we will be doing the umbrella sampling, at least we already know more or less what are the basic keywords for a QMMM calculations. Do you want to take a break, or for me it's really fine? So whatever you guys want to do. I think it will take other 20 minutes, so then we can continue and finish up. All right.
Okay, if you are not tired.
No. I'm okay. No, but it's okay. It's okay. No, I can continue. I can definitely continue, and it's basically almost done. Then if I think then if we have more time at the end, we can also do some things that people ask, so that at least we have some extra time at the end. So now we are here. We are in product. So what should we do now in order to run a QMMM calculation? Let's say that we want to start from the trajectory file, from the restart file of our product. So again, we copy our product.restart file in this time the QM folder. And we do is again the same for the system.parm7. Let's open the QMMM. So now here there is an extra folder.
Sorry, Sabrina talked to you in YouTube channel.
Okay.
I copy in the chat.
I pasted the, yeah, okay.
Sorry. Okay. Okay, sorry. So Sabrina is saying, don't understand what stripped, what's the function of strip. Yes, you're right, because I did not specify it. So strip means remove. So what it does is you you load the parm and the trajectory, and then you say, from this trajectory of which you have specified which files you want, or which frames you want. So let's do it again at this point. Parm system.parm7 trajin system dot, no, what was it, prod image.crd from 1 to 1 to 1. So here I'm saying again from frame 1 to frame 1 every 1 frame. Now strip water will basically remove all the water from my file, from the output file that I will want to extract. So this strip, now if we do the traj out and we call it, for example, system no water.pdb, now this file will actually have only the protein and the ligands, which are everything which is not water. So we stripped out the water. So let's check if this is true. So we do then go, sorry, it was fast. I did go, and then we do exit. And now we open the system no what. Now, in principle, this file, if we compare it to the system of before, here we see that it ends here. So it ends at the mol. If we open again instead the file that we had generated before with tlip, which is the system.pdb, now when we reach mol afterwards, then we have also our solvent. So basically this action removed from here to the end. So all the solvent out of my PDB. Okay. So then I think we copied everything in QMMM. Now let's open the QMMM input. The QMMM input is I copied, basically I copy pasted the same of the production run, but there is few other keywords which we need to add. Wait. This is not important, but at this point, okay. This one is basically, this is the extra keyword which is telling the program to turn on the QMMM part of the software. And therefore, so what is doing, what we're adding is this new part, which is basically the QMMM part, which is an extra part compared to our control. So here we have the control, and now we have this extra part. Here there is many different keywords which we can use. In this situation, I've chosen, since we're not actually doing the link atom approach, because we're actually taking the only in the QM mask. So the QM mask is actually telling me what is in the QM region. We're only taking my mol. Here the nomenclature is exactly the same as CPP trajectory. Therefore, we say QM mask, let's take the residue called mol, of which it has a charge of 0. Cutoff, we generate the cutoff for the region of the QM region of 8. And automatically, I think Amber uses an electrostatic embedding. So basically, all the point charges around all the MM region is taken as a point charge, and they're taken in the QM Hamiltonian as one electron integral. Then the QM theory, in this case, basically Amber has two possibilities: either to use the inner QM semi-empirical methods which they're developed to work with Amber, or we can use also extra softwares. So this is where finally we will be using Orca. In this case, with this kind of input, we're using the PM6, which is already taken in the QM theory. In fact, what I've written here, call external QM software, is wrong. So QM software, QM set of Amber. Okay, so now, since I want to just show you, we'll be doing only 20 steps. Okay, I'm seeing. So what is the difference? I'm seeing a question. What is the difference between the QM calculation initially done by Antechamber in the preparation of the ligand MOL2 file? So I believe that so for in Antechamber we've used this AM1 semi-empirical method, which basically is able to extract the charges. So I think that what it does a quick optimization of the ligand, and then it takes those charges and already provides them in your PDB, in the structure, in the MOL2 file structure that we are using then to generate the structure. Because in principle, the charge electrostatic potential charges that we generate with Antechamber will be then placed in the MOL2 file. In this situation now, we're actually doing a QMMM calculation. So basically, we have our QM region, which is treated at PM6 level, but also we have we're also taking care about we're also adding the environment, because I think that for the AM1 calculation of before of Antechamber, is actually doing a vacuum calculation. So because for the purpose of obtaining the electrostatic potential charges, we do it in the vacuum. So in this situation, instead, we're using the electrostatic embedding approach of which is already number. Okay. So now still we're not using Orca, we're just using PM6. Therefore, we will be doing the same calculation as before. So we do Sander minus O minus E minus QMM.in minus P system.pro7 minus C prod.rst minus X. No, let's do first minus R, since we always. How do we call it? QMM.rst minus X QMM.crd minus O QM.out minus inf QM.inf. The calculation is running. I believe it's already done. So this is the 20 steps, of course. Now I will show you. So here, yeah, this is all the printing. So we see that, yeah, the temperature is actually not too bad. And the first step is 400. This is only because the system is not really equilibrated, and also we're basically going from a force field calculation to a QM calculation, and this is basically also why we're actually here. We're not reading the velocities, but we're actually doing E rest equals 0 and NTX equal 1. So the calculation worked. Now, finally, then I wanted to show you also how we interface with Orca, for example. So let's copy again the prod.rst7 in Orca and the system in Orca. Okay, I believe that, yeah, in the structure, in the PDF where I did the structure of the tutorial, I think I did not include the Orca because I think I thought about it afterwards, after I create the image. Therefore, let's open it. So it's exactly the same file as before, but in this situation, we need to call the QM theory that we will be using will be used by this file called extern. Okay, so this extern will read this even extra part, which is this orc equal xtb. I believe that I'm missing. Let's see if it works. I think I'm missing this. Anyways, so basically here I could have also added, there is many keywords here. You can find it in the Amber manual. So method, in this case, since I'm using this tight binding method xtb, I will actually not specify the basis set, and in any other things. But in principle, here you can either use Orca if you want to use Orca, or Gauss if you want to use Gaussian, and there is also NWChem and many other ADF, QChem, TerraChem, and other softwares which you can interface with Amber tools. But also, let's say later on, my colleague Gustavo will tell you about the MoBio tools, which is a really nice software he developed in order to extract in a very elegant way all the from the trajectory, all the input files for a QM calculation, which is also interfaced with MOLCAS, and if you want to do excited state calculations, but we will talk about it later on. So let's see if it works.
Vito, sorry, there's
yes.
another question in YouTube channel, but I copied here.
Wait. So are the results obtained by PM6 comparable to Orca Gaussian? Can these be used for drone ligand molecule geometry optimization? Yeah, I think they're I mean, the PM6 of Amber, I believe that is comparable to a PM6 method of Gaussian or Orca. Of course, it's still a semi-empirical method, therefore, but for geometries, I saw that there is many semi-empirical methods which give really, really good results. One of those is this XCB that I showed before, especially used for transition state theory. And therefore, yeah, I think it's comparable. Then I don't know how I don't know if in Orca or Gaussian the PM6 is different. Probably it's different the way they wrote it. They wrote the code. But I don't understand what you mean by can be this used for drone ligand molecules. So for doing optimization, yeah, you can do these optimizations. Yes, you can do it. But I believe that if you want to do a geometry optimization of just your molecule, you can do it in vacuum. So then let's finish up by running the last command. Then next time we will talk also about science. But this time was just to show you all the possible commands, or at least few of those. Minus C prod.rst minus R, or let's call it orca.rst7 minus x orca.crd minus O orca. In fact, gave me an error because we're missing the final let's see if maybe it's this error, otherwise I will read again. Is actually another error, so let's see again the output. So it's telling me QM external, but QM equal different than 0. Therefore, I think the external interface does not currently support AWOLD or PME. Therefore, let's do orca.in and add the same keyword that we had before of QM eWorld equal 1, no, equal 0. Did not receive. I think it worked. Let's see. Error reading Orca output from. So current total energy not found for unsupported units. So let's see how we can solve this problem, and in case we will run this calculation the next time. Let's see, because I've already actually, no, I cannot open, of course, my folder. I believe that this calculation, this is the idea of this calculation, but I will solve it, and next time before doing the umbrella sampling, we will run again this calculation. Actually don't know, but I don't want to make you waste 20 minutes while I find the error. Therefore, I will solve the error, and then we can discuss the next time, and I will show you what is the correct way to run this calculation. So I believe that for today, we're basically done. And now let's go back to the slides. So those are some, since we're finishing, and like also I wasn't able to answer a few questions, I will suggest few books or articles which are really, really nice. My favorite book is this one, Molecular Modeling and for Principles and Application of Leach. Then this one is the Jensen of Computational Chemistry. Probably if you do quantum chemistry, you already read it. And the chapter 2 is about molecular mechanics. And then this one, this is another book similar to the Leach, where there is the chapter 1 actually, but all the book is really nice, but especially chapter 1 is a wonderful introduction to the concept of simulation. Now, for the YouTube people, I think, and also, yeah, you don't have these slides, so either you write down, or I will send those slides so that you can do the copy paste of those links. Otherwise, stop the video and write them down. Then for articles, those are my favorite articles to introduce you to the molecular dynamics world. One is this one, Biomolecular Modeling, Goals, Problems, and Perspectives. Then there are two really nice simulations. There's really nice articles about molecular dynamics. One is more practical, this one, and one is more intensive, more in-depth. It's also longer. And then this is an introduction to QMMM methods, which I think is a really, really nice review. And then finally, here I wrote homework, but you do whatever you want. This is if for next time that we will be doing umbrella sampling. This is, I think, my favorite paper about free energy calculations, because it goes from the definition of a partition function to all the possible ways in which we can do enhanced sampling methods. So I think that for today, unless there is any questions, we are basically done with the tutorial. So I will go back to the terminal, or no, I will stay here. Okay. Hello?
Question. No questions. We're very clear.
Very nice. Yeah, I don't know about that, but Antonio, if you have any suggestions for also for the next tutorials, if you think that there is something that you want, your students want to, or someone want to see more in depth, or I don't know, some other things also for next time, like, yeah, they can think about questions, and then we can discuss next time.
Okay. No, it was very nice today. It's difficult to run calculations and explain simultaneously.
Yeah, it's the first time. I think was intense. My brain is destroyed, but perfect.
You did a very good job. Thank you very much.
Thank you. Thank you, guys. I hope you actually run this calculation. If not, then yeah, just follow the PDF and the YouTube video. Probably you will be able to, by skipping some parts where I got blocked. So it's also faster because you probably YouTube you will see 2 hours and 40 minutes of video. You'll think, now I will never watch this. But yeah, it's you can speed it up.
There is a question. I'm going to copy it here to
Yeah.
you. Oops. Yes. Can you hear it?
Yep.
Okay.
Okay. I didn't. So with for multiple trajectories, so this means that let's suppose that you have 2 different coordinate files. Let's see, because I only created 1. So let's go back. Hopefully this will be wrong to do, but for example, CPP trajectory, parm system.parm7, then we can do either you can either do a for loop, or let's say you say get all the trajectories which finish with CRD. So in these situations, we only have prod.crd and prod.image, but this is a good way to actually get them all together, because now if we do the traj out, it will print together these 2 trajectories. So in case we have many different trajectories and we want to combine them, because for example, I don't know, a calculation stopped for some reason, but you still want to visualize it all together, this is a good way. You can either do it with this asterisk and then .crd, or you can do system.parm system.7 then trajin prod. So you execute, you get 1 by 1, and so you will put them in line as you want. So you do prod image.crd, and now traj out final.crd. And so now, if you see, now we will take the 100 from this prod.crd, and then also the 100 from prod image.crd. I hope this was the question.
Vito, I think I found the error in your input file of QMM.
Okay.
I think you're missing your an space in method, because I saw you input
The what am I missing?
a space after before method.
Here, like this.
Yes.
Let's see.
I saw you input file it in your computer. Sorry.
Okay. You saw it. Okay. In my okay. So in principle now it should work. No, it's given. I've never seen this error actually, because I tested this calculation before it worked. So yeah.
So the only difference is this between your
my calculation.
Yes.
Well, yeah, I don't know actually, but we will do. I will definitely do it next time.
Okay.
Wait. MPI. Yeah, no. Let's say. Because let me think. Yeah, I don't know, because Orca I installed Orca in my computer. Maybe it's not in the bash RC of this profile, so probably it's for that reason. Because in order to have it, you need to have a certain bash profile. I guess I will check also the Amber manual, because I don't remember. I've installed it a while ago. Okay.
Put another question to you.
Okay, so I'm talking. Okay, he said so I'm talking about single and multiple trajectory approach, and not different continued trajectory of a single run. So yeah, you can take about single and multiple trajectory approach. Well, in principle, if it has the same amount of atoms and the same the same amount of atoms, because in this case, then you can load your topology and then input all the trajectories you want. But for example, you cannot input a trajectory where you have stripped the water and where you have your normal trajectory. So for example, is this the, I hope this is the answer, but no, for example, if we have now the system.parm7, now we'll do it like this, trajin, let's say we did the prod, we stripped we have this one, we have this stripped trajectory. We will not be able to actually read it because there is a mismatch between the number of atoms. So in order to read these, you also need to strip the atoms out of the trajectory. So for example, you can do the parm7 like this, and then parm strip, which is, this is the command for the parm, so for the topology. So parm strip what? So this one is telling, make a topology file where you strip out all the waters. And so we see actually from the parm strip, it already gives an output. And then we do parm write out. So for the trajectory and for the topology, there are two different ways to input and output, to strip and to output the information. So we do system, how did we call system? No water.parm7. So now, for example, we see that this topology has a total number of 8,509, which is the total, which is protein plus molecule, while our normal system is with the water. If this was the answer, otherwise I can we can discuss. Like I can give you my email, and then we can because maybe I did not understand the question.
Yes, I think we are done by today, don't we?
Yes, yes. For today, then next time I will do the umbrella sampling. So probably we'll do the same creation of the structure. This time will be more simple and also smaller, so that we can run longer simulations. And then we will try to do this umbrella sampling, which is this enhanced sampling method that Juanco explained, and explain the setup and how to build those calculations.
Okay. So on Friday, we will start at 9 again, okay?
Tomorrow, yeah, Friday.
Yes, and 1 p.m. for you, okay?
Yes, yes, yeah, Friday, yes. Yeah, no, I heard tomorrow. Sorry, I was reading the question.
Okay.
Vito,
There is a question. I see. I just yeah, I see.
Sorry.
Suppose after the for each trajectory. Okay, how do I compare the different trajectory that I will be mapping different conformation? Well, depends on the I believe that depends on the observable that you want to compare, I guess. So in this case, you wouldn't need to do to put them all together, but you compare them one by one. So you do the topology is the same. You load the same, load the different trajectories. Mapping different conformation. So here you basically want to do a simulation from different random initial velocities. Well, this is a good way because it's always nice, I think, if you want to sample the phase space, in order instead of running 1,000 nanoseconds altogether, to run 100 nanoseconds from a different starting structure. If you want, for example, to see ligand binding, or if you want to probably observe a change in binding pockets, for example. So the comparison of the different trajectory, if you want, you can do with CPP trajectory. You can load your parm7 trajectory and get your observable that you want to compare, and do exactly the same the same actions and then compare whatever you want to compare, let's say. Okay,
so I thank you again, Vito, for your nice lecture.
Thank
you
you.
very much.
Okay, see you on Friday. Thank you, everyone.
Okay, yes. Have a nice evening for you in Europe.
Yes. Bye.
Bye-bye.
Nice day. Have a nice lunch as well.
Yeah, thank you.
Ciao.
Bye-bye.
Bye. Yeah, it's done. I think. Wait.